Welcome all of you. So we have been discussing about phase cycling, coherent pathway selection, etc. since last two or three classes about phase cycling, etc. In the last class, I introduced what is called pulse field gradients. We discussed a lot about what is a pulse field gradient, what happens if we apply a pulse field gradient to the static magnetic field. We understood it linearly varies across the entire sample volume along z axis. It is a z gradient we are applying. So gradient means that the magnetic field keeps on changing at different parts of the sample. Conventionally, it is assumed it is 0 at the center and increases above the first upper half and decreases below the lower half. And we also understood the precision will be faster in the upper half and than in the lower half. And we can think of this entire sample of the different slices, thickness of different slices. And then from slice to slice, then what is happening? The precision frequency keeps varying. But within this slice, all the spins will experience the same frequency. By increasing the stronger gradient, you can reduce the slice thickness. In which case, eventually you can see that everything can completely get defaced, and you are going to get a broad hump because entire sample the spins experience different Larmor frequencies, and the detected scene will be very, very broad. Then I also said we can apply a pulse, and I can even select the coherent order by applying gradients. Coherent pathway I can select by applying gradients also. We took a 90-degree pulse. Before the application of the pulse, we applied a gradient called G1 with a duration T1, and then apply a 90-degree pulse, and after you apply another pulse G2, gradient G2 with duration T2. And then our coherent pathway selection also we found out what should be the coherent pathway. Before that was P1 and afterwards P2. The phase that is acquired by the coherent order P1 during G1 was given as minus P into gamma into, we worked out everything into phi z is equal to gamma is gamma into Gz into T. Of course, G is the gradient into T. Same way we can get the phase for the coherent order after the pulse, and both of them are negative. It comes as minus P1 into phi into all those things. Can we, what happens if complete phase, if we take totally, if it is non-zero, what is going to happen? If it is non-zero, let us say, we saw that if it is non-zero, then what happens is complete signal will be decaying. The phase acquired is P1 into gamma into G1z into T. For P1 and then P2 is similar, both are negative. If you take the sum, if it is non-zero, there is a complete dephasing. On the other hand, if somehow the sum of the total phase acquired by P1 and P2 during G1 and G2 as 0, then what is going to happen is whatever is dephased can be completely rephased. That is what we discussed. How do you do the reversing? How do you do the reversing? Can we do the effect gradient completely reverse it, so that z rotation, if you reverse it, then what is going to happen is you can, whatever is dephased can be rephased also. You should, that means what we saw, we understood the G1 and G2 should be of the opposite sign. Before the application of the pulse, I will apply gradient G1. Identical gradient with the opposite sign if I apply after the pulse, what is going to happen? Before it will dephase, immediately after the pulse if I apply equal and opposite gradient, then it will rephase. Signal won't get nullified. This is a very interesting concept. Okay, so the effect of the z rotation is reversible. Okay, so how do you do the rephasing? First, now it is already dephased here. Inhomogeneity has already been created, and as you see different slices, the spins vectors are rotating or processing at different frequencies. The phases are different slices. Now this is after applying gradient Gz of phi. Now I am applying gradient minus Gz of phi. Opposite, equal and opposite. What should happen? it is like a spin echo. Exactly what happens is wherever the spins started, it will go back to the same place. It started like this earlier and it comes back to the same place again. This is what is called refacing. So the spins were completely homogeneous and processing in particular frequency. You created the inhomogeneity different slices of the sample, they are now processing at different frequencies. Their phases are different. And after some time, you apply equivalent opposite gradient with opposite sign, then spins will start going backwards. It reverses the rotation. The z rotation along z axis gets reversed and the spins start going back. So that means it will rephase exactly where they were before the application of gradient pulse. And this is what happens when you apply equivalent opposite strength of the gradient, originally dephased signal will become observable. Okay. Now the question is it true always? You may assume, are the nuclear spins of the molecules constant to a particular place? No. They will be undergoing motion, translational, they will be undergoing diffusion. There is a translational diffusion going on. This refacing is true only if the spins do not change their position along the z axis between two gradients. That is a very important point. But supposing you apply a pulse gradient and then start defacing, and when you apply a refacing gradient, it is assumed the spins have not moved from its original place. If they have moved because of translational diffusion, then refacing won't be proper. And in fact, this is the idea used to measure diffusion coefficients in NMR by doing an experiment called DOSE, which we are going to discuss if there is time at the end. Okay. So, as I said, we can select the pathway of a particular coherent pathway using gradients. It is possible. Like we used pulses using phase cycling, you can also use gradients and select it. Now we know what is the total phase acquired during both the gradient by the signal that we worked out, which is minus P1 into gamma into G1 Z into T1. Similarly for the P2, this is the total phase now we acquired. Okay. Now for the detectability signal, I told you this has to be equal, it should become 0. The total phase I made it 0. Now I equated this simple arithmetic which I did earlier. Now this turns out to be this. So if you do the arithmetic, what it says, G of G1 T1, because this gets cancelled, this gets cancelled out. Now G1 T1 over G2 T2 becomes minus of P2 over P1. This is what it is, because this minus when it comes this side became plus, but this still remains minus. So it is minus of P2 over P1. So G1 over G2 into G1 T1 over G2 T2 equal to minus of P2 by P1. So what do you understand from this? The strength of the gradient and the duration T1 have to be adjusted properly to refocus the D phase signal. That's what it is. We can adjust it. So that means if I adjust this G1 and G2 properly, then I can find out the ratio of P1 and P2. I can select the particular pathway. So required gradient ratio for a selection of a particular pathway can be worked out. Let us say I have a P2 is 2 and P1 is 1. Now P2 by P1 is minus 2. So you have to adjust G1 by G1 G2 and T1 T2 in such a way that ratio should become minus 2. Then you can select this pathway. I will show you one. Take for example, I want to select the pathway plus 2 to minus 1. This is a pathway I am choosing. Okay, this is my pathway plus 2 and then I want to select this one. This is my P1, this is my P2. P1 is equal to 2 and P2 is equal to minus 1. I want to choose this. According to my formula, G1 T1 or G2 T2 is equal to minus of P2 by P1. What is P1 here? P1 is equal to 2. Substitute here 2. What is P1 here? Minus 1. Minus of minus 1. So it will become 2. So the G1 T1 or G2 by T2 should be equal to 2. If this becomes 2, then 1:2 ratio. Okay. No, not 2, it is a half, I am sorry. It is 2 is in the denominator. Sorry, it is half. So G1 by G2 have the same duration if you make it. Now let us say T1 is equal to T2. I will adjust it. Then G1 by G2 has to be in the ratio 1:2 because G1 by G2 ratio is equal to half. As a consequence, what you have to do is G1 or G2 if you take, G2 should be equal to 2 times G1. So if you adjust the ratio of G1 by G2, keeping the duration T1 and T2 identical for both, you can choose this particular pathway for P1 is equal to 2 and P2 is equal to -1. Okay. For the pathway, I want to select -2 to -1, let us say. How do I do that? P1 is -2 and P2 is -1. So now we know the simple formula. G1 T1 divided by G2 T2 is equal to minus of P2 by P1. Okay. This is again P2 is -2, P1 is -1. So it turns out to be minus of, because this minus is still there. So this minus you may cancel it, but this minus is still there, so it is minus of. So now in this case G1 G2 have the same duration, but their strength have to be opposite. The sign have to be opposite. In the previous example, remember G1 was equal to G2, you remember, if you see here 1:2 ratio. But here the same 1:2 ratio, but they should be opposite, 1:-2. See, G1 should be equal to minus of 2G. So G1 should be equal to 2 times G2. Then I can select this particular pathway from P1 is equal to -2 to P2 which is equal to -1. So this is a very easy, and in this case very simple. In the homonuclear case, gamma gets cancelled out, Z gets cancelled out. All you have to deal with is G1 T1 over G2 into 2 to equal minus of P2 by P1. All you have to know is if you keep the delays identical, T1 and T2 duration, keep it identical, G1 G2 ratio you can find out by particular ratio of the pathway what you want. Okay. So that is easy. But in the case of heteronuclear case, it is not so simple. It is slightly different, because as you know, gammas are different. When the gammas are different, you cannot consider just like that so simple. So we have to work it out in a slightly different way. So how do we select the pathway for heteronuclear spins? Now I will take, one is I spin, other is S spin. Earlier I didn't bother, both are homonuclear. Now I am going to put a diagram like this. This is I spin. Notice I have not applied any pulse on the I spin. No need to apply pulse spin, but they are coupled, it is there. And this is S spin. S spin, on the S spin I am applying 90-degree pulse. The gradient before the pulse is G1 is T1. Gradient after the pulse is G2 for the duration T2. Please understand, pulse is not applied only on I spin, but the gradient is applied for both. Gradient is general, it is not on a particular spin. So gradient is applied. Here pulse can be applied on a particular nuclei. Here gradient is applied just like that for everything. Now coherent orders are separate for each heteronuclear spin. The coherent order for this is different and the coherent order for S is different. They are not same. Coherent orders for I and coherent order for S both are different. In this case, I deliberately take, since I have not applied any pulse on the I spin, I want only -1 pathway. That is what my detection. I want to detect, let us say, -1. That's finally what, if I detect I spin, I look for -1 pathway. So this is my pathway, let us say. And for the S spin, my pathway is +1 to 0. Please understand. For the I spin, the pathway is -1 throughout. For S spin, pathway is +1 for during G1 and pathway is -1 during G2. See the difference. For both the nuclear pathways are different. For one of the nuclei Pi which I have taken -1 as the pathway for my detection, and it is same for both G1 and G2. For both the during gradient time, the pathway for this is -1. As far as the S spin is concerned, during G1 the pathway is +1, during G2 pathway is 0. This all the logic we have to understand. Now we calculate the phase, spatially dependent phase from each of this gradient now. We know how to calculate the phase, that is already given. Earlier if gammas were different, you could have taken individually and added. Now gammas are, earlier gammas were same, now gammas are different now. Now pi gamma is multiplication factor here, this is gz into t. So earlier you did pi, I was not there, p1 gamma gz t we wrote. This is 5z. This was the phase acquired for a particular coherent order, that we knew. But remember, now we also have heteronuclei present. So what I am going to do is I write a simple equation, pi gamma I plus ps gamma s, both in brackets multiplied by g. Of course you can write individually. I have taken gzc out because that comes as a product for both the terms here, and therefore negative sign continues. Now note, in the heteronuclear case, Gauss-Magnetic ratios are not identical, they are different. Gamma for carbon is 4 times less than that of proton, you know that. So that is why you have to explicitly calculate now. Now we have to work out the total phase for both the heteronuclear spins for each gradient. That each gradient you have to work out what is the total phase. For G1 gradient, pi is equal to -1 for I spin and ps is +1 for S spin. So or in other words, we will write like this simple. There is no pulse on I spin. Since there is no pulse on I spin, the coherence order remains same throughout. So because I have not applied anything, I have chosen -1 pathway. So pi is -1 for gradient G1 and is also -1 for gradient G2. I have not changed it. It is continuously, I have taken only one pathway. What about PS? For the PS, I took the pathway 1 to 0. So for PS, for G1 pathways, this PS is 1 and it is 0 for G2, because during G1 the pathway was +1, the coherent order was +1, and then during G2 the coherent order was 0. So remember, the coherent order was -1 for pi all through, both during G1 and G2, whereas for S spin the coherent order is +1 during the gradient G1 and it is 0 for the gradient G2. With this, now total phase acquired you calculate. For now you know, for the phi z1 first time for the gradient 1, what is the phase acquired? For the gradient 1, phase acquired is pi gamma I, ps gamma s. Now pi is -1 here, ps is +1, add it up. Now make the simple calculation. Phi z for the gradient 1 turns out to be -1 into gamma I, 1 into gamma s, this one. This boils down to simple phi z1 for the gradient 1, the phase acquired is gamma I minus gamma s into G1 ZT1. That is for the first this thing we worked out, first gradient, because both the spins are there now, both heteronuclei are there. Similarly, work out for phi z2 for the gradient 2. For the gradient 2, we know that P1 continues to be still -1, whereas PS we have chosen pathway from +1 to 0. What is the total phase acquired now due to gradient G2? This is same. Now you have to substitute like this for PA and PS. PA is equal to -1, PS is 0 now. Previous it was +1 for G1, now for G2 is 0. Work it out. Simple arithmetic. Plug in these values here. For phi z2, then it turns out to be phi z2 equal to gamma I G2 ZD2. Okay, that this is 0. So gamma s term does not come into the picture here at all. We calculated now phase acquired during G1 and phase acquired during G2. Both are known. What is the refocusing condition? Sum of both the phases should be 0. In which case we can get the detectable signal. So phi z1 plus phi z2 should be equal to 0. Put this condition now. We worked out for phi z1. It is gamma A gamma s into G1 ZT1 plus gamma I G2 ZT2, this is equal to 0. Do the simple jugglery by rearranging the terms. Now G1 T1 by G2 T2 turns out to be gamma I divided by this thing, because of course both are positive here, this negative sign is carried forward. This can be further simplified like this. You divide this by gamma I, then this will become 1 over 1 minus gamma S into gamma I. What is gamma S and gamma I? Take for example carbon 13 and proton. Carbon 13 gamma is 4 times less than that of proton. Plug that value here. Of course, to remove the minus sign, this was put in the reverse order now. So instead of 1 minus gamma I, it is gamma S over gamma I, over gamma I minus n was written. So this minus sign was taken out. So now for I is equal to 1H and S equal to carbon 13, if these two are the heteronuclei, this ratio turns out to be 0.252, because gamma I of proton is 4 times nearly larger than that of carbon. So this ratio turns out to be 0.252. So put it here, then it turns out to be the ratio of, if you maintain the duration T1 exactly equal to T2, you do not change the duration, then what is that you have to calculate? G1 should be equal to minus 1.337 times G2. So what you did, we know what is the ratio of G1 and G2 to be chosen, so that you will select the particular pathway, that is the coherence pathway remains minus 1 all through for gamma I and plus 1 to 0 for S spin, so that what is going to happen is when you select the pathway during the G1, you are going to have minus 1 for Pi, and during G2 also minus 1 for Pi, and for the S spin it is plus 1 during Gi, it is 0 during plus 1 during G1 and it is 0 during G2. So this is what you have to do, is make a simple calculation and then now adjust G1 G2 ratio. This is the phase cycling, this is the coherent pathway you are going to select. Remember, analog, it is exactly analogous to what you do in the by adjusting the pulse phase and receiver phase. By doing phase cycling, you can get the particular pathway. Same thing you can do by adjusting the gradient ratios between G1 and G2. This is what happens, and this is a simple example we have chosen. Let us take another simple example now. Another simple example is now this one. For Pi, it is plus 1 during T1 and it is minus 1 during T2, that is plus 1 during gradient 1, minus 1 during gradient 2. This is for gradient 1, this is during gradient 2. What about PS? What is the pathway for S? S is during the gradient 1, this is plus 1. During gradient G2, this is 0. Now, unlike in the previous example where minus 1 was running continuously for during G1 and G2 for I spin, now I have changed it. G1 and G2 are different for both, for the P1 and Pi and PS are different for both G1 and G2 for the both the gradients. So now using this one, we will go back and select the pathway. Now pathway chosen for I is what? Clearly you see plus 1 to minus 1. So Pi is 1 for G1 and minus 1 for G2. So what is the pathway chosen for S spin? It is plus 1 for G1 and 0 for G2. This is very well known now. We have already worked out. What is the total phase during G1 now? That is total phase during this G1 is phi zeta phi is equal to Pi into gamma I minus of plus Ps gamma S into G1 Z T1. Plug in the values now. What is Pi for the G1 is 1 and this one you put it 1. So it is turning out to be Pi is equal to 1, Ps is equal to plus 1. Substitute in this equation, what you are going to get this? Minus of 1 star gamma I, 1 star gamma S. So both it will remain as minus of gamma I plus gamma S over into G1 ZT1. This is what you are going to get. See, this is what you are going to get. For the phase 1 during the gradient 1, the phase turns out to be minus of gamma I plus gamma S into G of into G1 ZT1. Okay. So that is what is this. Work out the similarly the phase for the gradient G2. For the gradient G2, we know it went from we chose the pathway from +1 to -1. So now for gradient G2, Pi is -1 for I spin and Ps is 0, that is for S spin. Substitute it in this equation now. The total phase acquired again for phi 2 is this one. Now in this case substitute Py as -1, Ps as 0. So this term will go, and what you are going to get is minus of gamma I into G2 ZT2. This is the phase acquired during G2 by together, total phase acquired. Okay. So phi Z turns out to be this one, phi Z2. We already calculated what is phi Z1. We know that. So what you have to do now? For refocusing condition, phi Z1 plus phi Z2 should be equal to 0. Now when we put that condition, this is the phi Z1, this is phi Z2. So now minus is there, take it this side, then it turns out to be a very simple equation. Do the simple arithmetic now. Now you take out Z will go, but gamma you cannot cancel because heteronuclei. Now G of, okay, it is written this way, GT1 over G1 T1 divided by G1 G2 T2 is equal to now gamma I over gamma I plus gamma S. That is a simple arithmetic. So now if you know the ratio, if I put again T1 equal to T2, the duration of the gradient, if I keep it constant, then G1 by G2 ratio should be equal to this. Again you know what is, divide this by gamma I, 1 over 1 plus gamma S by gamma S 0.225. Now you take 1 over 1.225, now it is going to be a different number. So now this the number what you have to choose is entirely different, so that the pathway chosen for I spin and pathway chosen for S spin are different now. As a consequence, you can find out what is the G1 by G2 ratio. If you, of course you can vary T1 and T2 also, it is your choice, but then mathematics is going to be clumsy. You need to calculate the numbers. So best thing is keep the duration constant of the gradients. If you keep the durations constant, what you are going to get is ratio of G1 by T2, which is given as in terms of gammas of both the nuclei here. And once you know gamma of carbon 13 and proton, we took the example, we worked out, and 2 examples we can select the particular chosen pathway. Now what will happen if I have a nitrogen instead of a proton? That's all you have to do is gamma S is different. Gamma S is 15 times, 15N is 10 times smaller. Nitrogen 15 gamma approximately 10 times smaller. Then it you work it out. Then G1 G2 becomes smaller. Same pathway you can select. Now instead of proton and carbon, it is going to be proton and nitrogen. That is also possible. So you don't have to do anything. Let us say you have a multi-nuclear system. You want to select the pathway for proton carbon. You worked out. You decide to change, select the same pathway for proton nitrogen. All you have to do is simply know the gamma of the nitrogen, you know, recalculate the value, simply adjust the G1 G2 values. That's all. Then automatically you will select the identical pathway for proton nitrogen also. So this is what is the thing which I was trying to tell you. Now since the time is up, I want to stop here. But what I wanted to tell you is, using gradients, you can select the particular pathway. Coherent pathway you can select. Now we took the example of the homonuclear spins. We found out how we can select pathway. In the case of the homonuclear spins, very easily we can calculate G1 T1 by divided by G2 T2 and what is the ratio of gammas. That we worked out. But if you keep the duration constant G1 by G2, Gamma is same there. In the case of homonuclear case, it was a simple number you worked out. We can select a particular pathway. But in the heteronuclear case, it is not similar because gammas are different. You have to calculate the phi 1 phase acquired during G1 for both the spins individually, like for during gradient G1, phase acquired by I spin, phase acquired by S spin have to be taken together, and then similarly calculate the phase acquired by I spin and the phase acquired by the S spin during the gradient G2. For the refocusing condition, the phase phi z1 during gradient 1 plus phi z2 during gradient 2 should be equal to 0. Now equal this condition. You do simple jugglery of arithmetic, not a great thing. Then you find out what is the G1 by G2 ratio. Adjust that number. You can select a particular pathway for heteronuclear spin also. And we took the example of for proton carbon, and we chose two examples, one where I spin there was no pulse at all, and we chose the pathway -1, and S spin was going from +1 to -1 to 0. Another case, I spin was going from +1 to -1 and S spin was going from +1 to 0, like that. Some examples we took and we worked out, and we saw how we can choose the perfectly we can choose a coherent pathway even in heteronuclear spin case. So with this I am going to stop now. We will come back and continue further about this gradient, little bit I am going to tell you, and then of course we can use this gradient in many multiple experiments to choose a particular pathway. When since I have not introduced 2D, I am not taking the example of 2D pulse sequences. After that, we will take example of 1 or 2, for example, decay of Cauchy, NOC or some Cauchy like that, and then find out a particular pathway selection, how we can do both by phase cycling and also by gradients. We will come to that later. So right now I am going to stop here. We will continue with gradient little bit more I have to discuss next in the next class. Afterwards what I will do is we will go to a different topic. Thank you very much.